Right. Let's move on again, looking at some aspects of electrochemistry. Okay. In this part, I would like you to understand the application of Pobe diagrams in hydrometallurgy. That's the portion that I would want you to have an appreciation. Right. So as we have said before, As we have said before, the chemistry of hydrometallurgy basically can be said to be either a proton exchange or an electron exchange reaction. If it is a proton exchange, then it is an acid-base reaction. If it is an exchange reaction, then it is termed to be a redox reaction. Okay. Now, we said we use this basis of proton exchange or electron exchange in reaction, and it gives us the ability to construct Pobe diagrams based on the potential that is created if it is an electron exchange, and based on the pH that is affected by the proton exchange that happens in these hydrometallurgical reactions. So we are able now to construct what are called these Pobe diagrams, your potential versus your pH, right? So, however, if you have seen that they are quite useful in determining a lot of hydro metallurgy principles. They're quite useful indeed. However, they've also got some certain disadvantages. Okay, so one of the disadvantages of your Pobe diagram is that they only provide thermodynamic data, right? Thermodynamic data, so showing that this reaction can okay. They're also showing that in this region this species is also very stable in this in this region. However, they do not provide any information on the rate of reaction. Okay, so that's one disadvantage. There also another disadvantage is that mostly Pobe diagrams are dealt with using pure metals, which is ideally not the case, because when you are processing, you actually have got ores and concentrate, and you actually have even very low grade values in your in your slurry, or whatever, in your medium for conducting these hydrometallurgical processes. So that's another disadvantage, is we are working with pure metals, but unlike the case we are working, but in actual fact, in practice, you have got very low grade of your ore if you are comparing with a pure metal. Okay, then there are other properties now, such as porosity, such as thickness, such as adherence to substrates, that are actually not even considered when you are doing your EH/pH diagram. So, in brief, these are some of the disadvantages of your Pobe diagrams. However, need I say that, as you have seen, that these the advantages of these systems, they far outweigh the limitations that are actually seen. Why? Because you can actually plan, you can actually have an idea of where to start. Remember, we said one of the application is in design of leaching principles. You exactly know which area is stable for your leaching to occur. You know that area, and when you have done that, you start by then, and then you can now move on to other aspects, such as your rate of reaction, such as the porosity, thickness, or whatever other properties that might need to look at. But you have a proper concrete starting point for designing your hydrometallurgical processes, using especially your leaching processes, using your Pobe diagrams. Okay, right. Now let's look at the metastability of your of species. Now, as we said before, Pobe diagrams only show what is the most predominant species, or the most stable species. As we say, it is the only the most predominant or the most stable species that is shown. However, it does not mean that it is the only species that is available in that region. It only means that it is the most dominant species. So there are other species that are also existing in that area or in that phase. However, these are called metastable species, and they are usually conveniently not shown or indicated on your EHPH diagram. So consider this case now for your sulfur water system. You can see the predominant species here, your H2S, your SO4, HS, your HSO4 minus, your S2 minus. These are the showing now the most predominant species in various conditions of your potential and pH. Now, if we now introduce the metastable species, you can see that in this region, where we thought that our SO4 is the most stable region, we can see that there are so many other complexes that are existing in this region, as shown here. There are so many other species that are available in this species, and we can actually see them when we we can actually construct Pobe diagrams using some softwares. So you can see that if we eliminate this SO4, we are able now to see all these other metastable species that are masked or enveloped by the predominant SO4. So they've got some certain dynamics that they also play in the kinetics or in how the system works. Because if we only assume that, for example, in this stage only SO4 2 minus is available, then you might ignore the effect of these metastable species, which in certain reactions might also affect the system at large. Okay, right. So here, they're actually what are called speciation diagrams. Okay, so speciation diagrams, they also show some some metastable species that also can be masked. Okay, so here this is a this is a showing a metastability case of your H2O diagram. So remember, here your S can exist as S6 or S2 minus. Okay, so what is metastability? What is this speciation diagram showing us? These speciation diagrams are showing us in the same oxidation state, an element can actually form different species depending on the pH of the solution. So you can see here, this is the starting point of your S6 plus. Okay, so we can see that this H2SO4 6.5 water, as you increase your pH, it goes down. Okay, its concentration actually goes down. As it goes down, the concentration of HSO4 also begins to rise. Okay, but as you continue to increase your pH, it also begins to fall down, and when it falls down, then your sulfate begins to increase, your SO4 2 minus. So this is some of the metastability cases for your S6 plus. The same again for your S2 minus. You can see that at lower pH here, your S2 minus exists as H2S. If you increase your pH here, it dissolves out of solution, or it becomes unstable, and your HS minus becomes stable. When you increase again your pH, it falls down, and S2 minus becomes stable. Okay, so this is very important, because you need to know what are the species that are formed by S2, whilst it is an S2 minus species, but you can see that it is formed different species altogether, even if it is in the same oxidation state. So you need to understand these in speciation diagrams and also in your EHPH by delving deeper into understanding what effect does this have on my system, instead of just looking at the S2 minus or maybe the S6 plus ion only. You need to understand the kind of species that it forms when you increase or you change your parameters, such as your pH. Okay, right. So let's look at the leaching of copper sulfides. Okay, in brief. So you see that almost 80%, if not more, of the copper that is mined and processed in the world is actually in sulfide state. Well, the rest is in your oxide. Then it can be actually leached much more easy by your, for example, by your sulfuric acid. But most of it occurs in sulfide, and having occurred as a sulfide, actually, in order for you to concentrate it, you have to use the flotation technique. Okay, that's for you to concentrate these sulfides. And after flotation, using your different kind of collectors, frothers, etc., this concentrate is typically treated by pyrometallurgy. Okay, so in the case of pyrometallurgical processing of your copper sulfides, what you're simply doing in pyrometallurgy, you're simply conducting the oxidation of S2 minus and producing your SO2, your sulfur dioxide gas mostly. Okay, so this is then used for the production of your sulfuric acid as a byproduct of the treatment of the sulfide concentrates. Okay, so this is the issue, environmental issue, that pyrometallurgy processing produces the toxic SO2 gas. However, as the technology has increased in recent years, we can say that the scrubbing systems or the cleaning systems of pyrometallurgy are actually very much efficient in these days, such that there is very little or no SO2 that is actually released into the system. Okay, right. So there are several leaching procedures of these sulfides that have been proposed. Why? Because when you now do a leaching, it means that you have eliminated this production of SO2 gas. Okay, so this is actually one of the most important detail, one of the most important reasons why you should leach these sulfides. Okay, this is one of the most important reasons, environmental reasons, why you should do hydrometallurgical route of this processing of these sulfides. Okay, so your 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 hydrometallurgy now involves the oxidation of your S2 minus with your oxidizing agents such as your oxygen and your Fe3 plus, and you want to produce SO42 minus the sulfate or the S0. That's the benefit of using hydrometallurgy. In pyrometallurgy, you are producing SO2 gas, which is really unwanted. Okay, so here is the EHPH diagram of your copper, and you want to decide of your copper sulfide. You want to decide which is the most conducive route for processing of your ore, of your copper sulfide ore. So using this EHPH diagram on your left, you can now decide which route you want to go. So first of all, you can choose to go reducing conditions or oxidizing conditions. Okay, based on this diagram here. So let's divide this into something like this. Okay, we know what these regions are: oxidizing, reducing conditions, basic, and acidic conditions. So here, let's say you now this is your your diagram. Sorry, here. Okay, so in reducing conditions, okay, in reducing conditions, this is below reducing conditions. For your memory, it is what? Below zero. These are your reducing conditions that are below this line of E0. You'll be in reducing condition. So in reducing conditions, if you take in the reducing acidic conditions here, reducing acid conditions here, it means that you produce H2S gas, which is unwanted. Okay, you produce H2S, so it might not be a good idea to leach using in these conditions. How about if we say we want to use reducing conditions, but this time in basic? So you produce the HS or the S2 minus. These are the basic conditions. That is what you you produce. Okay, that is the HS minus and S2 minus. Those are the stable species in those reducing basic conditions. How about maybe you decide you want to go oxidizing conditions? So it means that you are using your potential which is above zero. So if you use a potential above zero, then in acidic conditions, so you're producing your S0 here, which is shown here, and also probably your SHSO4 minus here. This is your acidic oxidizing conditions. However, if you use basic oxidizing conditions, you have here your SO4 2 minus, which is probably one of the most environmentally friendly processes that you can actually use in this case, because you are producing the sulfite ion. Okay, right. So this is how you design your leaching profile for your copper sulfide. You first of all now go deeper into which one that you can select to use. First of all, you can now find the advantages and disadvantages of the systems that you prefer to use. Okay. Right. Now let's consider the leaching of gold in aqueous solutions. Now, if we look at the the gold water system, we can uh, we can see that you can see that the soluble species of gold are not stable within most of the regions of water. There's just a small region here where gold forms an ion, which is stable, and so what does this mean? It means that the oxidation of gold, um, it means that the oxidation of gold by oxygen is thermodynamically viable only at very small this small range where you've got your high potential and your high pH values. Well, in practice, this would be a very good thing if it was possible in practice, really, such that your water is able to dissolve your gold. However, in practice, it's not as simple as that. Okay. Then also, it is actually also not a good idea to operate. It's actually not a good idea to operate outside the regions of water stability. So there are several reasons that you can find out why it is actually not a good idea to operate in regions outside the water stability. Okay, right. So what are we trying to drive home here? So let's continue this leaching of gold in your cyanide solution. So cyanide forms many complexes with with gold. Okay, so there is increase in gold solubility when the Au Cn2 plus complex is formed. Okay, then this complex is responsible for stabilizing the gold ion, which is what we want, the gold in solution. We do not want the gold in solid. We want at zero. We do not want this. We want the gold occurring as Au plus. That simply means that the gold has been leached. Okay, so when you look at your regions here, the EHPH diagram on the left, you can see that if you eliminate some of the things, you can actually see that the gold cyanides can actually be formed in these regions. Okay, of that's the region of stability of AuCN2 minus. However, when you now include certain information, because it is not only the AuCN system that occurs, you now have got other species at play, such as your hydrogen. You begin to see that the hydrogen cyanide here, there is below a certain pH, you are now forming HCN here in this range, which is highly unwanted. So you find that in this above this certain pH, you have got your Cn minus, which is what we want to stabilize the gold plus ion. Okay, so this is what we want here. This sort of like this range. This is what you want. You now marry the cyanide what you call the cyanide region of predominance, and then the gold region of predominance with complexing with iron. So you find that this is the in this case, using these conditions, this would be the area of choice to target now when you want maximum gold leaching in the in the in the in the cyanidation system. Okay. Okay, right. So, at low concentrations of cyanide, you find that your AuCN can your AuCN2 minus can form, but there is also formation of insoluble AuCN compound. This is not this is actually insoluble, so this is actually a solid. So when this unwanted when this unwanted compound forms, it can actually passivate the gold. So you need to avoid some low concentrations of your cyanide. So you find that at times you want to use cyanide and then use it in low concentrations. And when you use in low concentrations, you find that your gold recovery is actually there's actually no gold recovery, or it is very very minimum, and you wonder what's happening to the cyanide. It is because in these low concentrations here, you are forming, instead of forming this AuCN2 minus, you are actually forming AuCN, and then this AuCN is really it's this one is really detrimental here, and you don't want it to be formed. But also at the same time, it's also stable, maybe in acidic conditions, so you might maybe get away with it. Okay, right. So as we said before, the available species in a system are quite many. Though we are saying maybe it's a gold cyanide system, but there are so many species that are interacting in the system. Your gold ore might contain copper. Your gold ore might contain antimony. Your gold ore might contain even iron. Your gold ore might contain different species that either are wanted or unwanted. And actually, these species now, they make the process of cyanidation, which seems actually very simple when you look at the Elsness equation. You need your cyanide, you need your oxygen, but it tends to be very very complex now when you have got some species that are unwanted in the system. They actually affect now the desired outcome. And you expect your gold to be leached very much easily. It is not, because you are now dealing with what you now, of course, what you know as the refractory gold ores. So the reaction of choice is actually one in many other reactions that are actually progressing in a reactor. Okay, it is actually one in many other reactions that are progressing in a reactor. There are so many background reactions that are also occurring when you are doing your process. Remember, when you're dealing with your refractory gold ores, okay, there can be three ways in which your ores can be refractory. Main three ways. There may be the others, right? First of all, in terms of in terms of chemical refractoriness. So you can find that you have got compounds or minerals that eat up your oxygen. Okay, then you've got your compounds that eat up your cyanide. Okay, then first and last, you can actually even have compounds that form a jacketing layer. Okay, that form a jacketing layer or a passivating layer. So you find that all these are happening in the background. Even if they're happening in the background, you realize now that your processes are actually affected. Why? Your oxygen is being consumed, your cyanide is being consumed by your cyanosides. Then instead again of your gold to be leached into solution, it forms what is called as a jacket effect. There is a sulfide layer that forms on the surface of the gold. This is quite prominent with your stibnite. Stibnite is one of the most troublesome elements, one of the most troublesome minerals in the hydrometallurgical processes, especially when you're doing your cyanidation. It actually has got properties to do all these three adverse effects on your system. So what we are simply saying is that there are so many background reactions that can occur in a system that you need to be aware of. Even if your Pobe diagram has shown you the predominant species, etc., there are so many other metastable phases, and so many speciation that are happening, species that are high in concentration, they reduce when you increase your pH. Other species come into play. Okay, so you need to understand all that. So for example, on the left here, in acidic, you're saying your gold is existing together with H2S in acidic conditions there, which is really unwanted. Then we've got maybe here you have got the stability region of your SO4 minus. Then here you've got also your stability region of your S2 minus in the in high pH. So you need to know exactly what effect all these species have when you are doing your leaching. Now, for example, again, if you look again on the right, you've got your copper system. Okay, so copper is also one of the most detrimental metal elements that are actually problematic also in gold leaching. Okay, so you find that copper also forms stable complexes now with your cyanides. So it is a very strong cyanide. When instead of the cyanide to be a forming complex with gold, it also competes with copper and forms some stable complex with copper. So you now know that in principle, in general, the stability, the stable phases of your copper when it forms your cyanide generally are your monovalent and your divalent or your dicupro cyanocydes or cyanocomplexes. So these ones are very detrimental because they follow the path of your gold cyanide complex as we know it. So you need now to avoid the regions where some of these here some of these complexes such as the CN2 minus form. You need to avoid these regions. Okay, so what in terms of this reaction, what you do, so you really find that in as a way to treat the copper, most of the gold plants, you would actually what do? They actually increase the working pH of the system. So what exactly are they trying to do when you now increase the pH of the system? When you increase the pH of the system, you are now trying to form probably your copper a trivalent or your copper tetravalent cyanocomplexes. Now these complexes they are actually not able, or they slightly tend to they actually tend not to adsorb on the carbon, or if they adsorb, they easily dissolve from the carbon. So if you're working at a high pH and you've got your sort of like your tetra and then your trivalent cyano complexes, you can actually get away with the system having lots of copper, but you'll be also able to leach your gold. Of course, you need to do this in a high concentration of copper, and then we know that as a rule of thumb, your concentration of your let's say concentration of your cyanide over your concentration of your copper must be actually be greater or equal to 4. That's the rule of thumb, usually greater than or equal to 4. That's the rule of thumb when you're dealing with this copper problem, this copper cyanide. You can actually do some proper leaching of gold, even if copper is present in solution. Right. So this is just this graph here is just an illustration. If you using the conditions that you actually be, if you try to draw a diagram with all the complexes, maybe this one omitted the CU CN4 minus, maybe somewhere you find the CU CN4 minus somewhere there. You know now that maybe at a slightly higher pH, this is where my system is supposed to work, and you've produced actually some good results. Okay. Right. So what are some of the questions of importance that you need to consider when leaching gold in solutions? You need to understand that you need to understand the driving force for the reactions. you need to understand the minimum cyanide concentrations for reactions to be thermodynamically stable. So it means that you need to understand your dosages, your reagent regime. For example, your optimum sodium cyanide for your oxygen that is available, because according to the Snell's equation, you definitely need some cyanide and some oxygen for your system to be optimum. If you use high cyanide concentration without oxygen, then the reaction might not be in terms of the kinetics of the reaction might actually be very much detrimental. You also need to know the pH that is safe for environmental operation. Okay, you need to environment, both the people, maybe also the equipment, and also the environment at large. Okay, then you need to know the stability of the lixiviant under your leach conditions. In this case, your cyanide, where is it very much stable? You want your cyanide always to be in Cn minus. That's where you want for it to be able to leach the gold and make the Au plus ion stable. That is what you want. Then also you need to know that if is my lixiviant recyclable. Those are some of the questions that you need to be asking when you consider leaching gold in solution. For example, we said now this system, if you have copper, you have got lots of concentration of copper in the system, and we say that it is because copper is a cyanide. You need to understand that how to what extent of recycling of my lixiviant should I do, because if it also the copper now, if it is in high concentration, then it will also now begin to absorb. It also begin now to follow even the elution electrowinning circuit, and you need to avoid that. Okay, right. So okay, identify a problem that you will thoroughly analyze using the technique you studied so far, and propose solutions on what you have studied. Okay, give a background of the process and outline several problems that you have researched, and select one problem and analyze the tools learned so far. Okay, so this one, maybe only 5 pages. Okay, so I would like you to identify a problem in leaching of gold or copper. Then you thoroughly analyze using the techniques, especially of your electrochemistry that you would have studied already. Then propose new solutions based on the electrochemistry understanding that you now have. Okay, so in this research, give a brief background of the process, outline several problems that you have researched, and select one problem that you can now analyze using the electrochemical processes, and then propose new solutions. The idea of this research assignment is for you to gain new knowledge. Okay, I'd like you to gain new knowledge and new understanding. The more you delve deeper, the more you understand. So give yourself time to go deeper and find new knowledge in this aspect. Okay, thank you. Maybe no need for you to do this because of time. Okay.